Climate change is a hot topic that affects each one of us.
Um,
We all know about global warming, about how human activities contribute to continuous temperature increase in every place around the world. We all hear about the ice melting, about the rising sea levels, about extreme weather conditions like floods and hurricanes. What can we do as software engineers to help prevent climate change? Are there any actions that we can take in our daily jobs in order to build software that is friendly to the environment? Stay with me and find out how you can make a real impact in your work by building sustainable software. My name is Yannis Kolaxis, and I am a software architect working for Atos in Athens, Greece. I love learning about new technologies, trying to come up with innovative ways of how we can use them to solve daily problems. Last year, I was awarded the first prize at Atos Innovation Week for coming up with the most innovative idea. I am an inventor, I have filed several patents, and you can visit my blog to read one of my articles on how you can also become an inventor. I've been building software applications throughout my career, previously working for IBM and Siemens. I am a speaker, and although nowadays I don't get the chance to speak at physical conferences, you know why? I have previously had the chance to speak at several conferences, including Oracle Code One in San Francisco, USA, back in 2019. Follow me on Twitter to learn more. First, I'd like to make sure that we all have a common understanding of the problem. What causes climate change? Human activities, like burning fuels, produce carbon dioxide and other gases known as greenhouse gases. These gases are present in Earth's atmosphere and they trap heat. They let the sunlight pass through the atmosphere, but they prevent the heat that the sunlight brings from leaving the atmosphere. They can be thought of as a blanket wrapped around the Earth. To prevent climate change, we clearly need to reduce the carbon emissions, the emissions of greenhouse gases. For simplicity, we will be referring to greenhouse gas emissions as carbon emissions. Who are the key contributors to carbon emissions? According to the International Energy Agency, electricity and heat producers are the top contributors by accounting for 42% of the global carbon emissions in 2018. Can you guess how this relates to our work as software engineers? As software engineers, we build applications that run on servers. These servers are hosted in data centers that consume electricity. Our users, our clients, rely on a network, most commonly the internet, to access our applications and exchange data. According to the International Energy Agency, approximately 2% of the global electricity is consumed by data centers and data networks, with data networks consuming more electricity than data centers. Clearly, these data tell us that we need to make our software applications more energy efficient so that they consume less energy and therefore emit less carbon. Nowadays, we all use applications like Google Maps to calculate the best route from point A to point B. The best route to our destination may be the one with the shortest distance or the fastest one. Google Maps allow us to calculate the most fuel-efficient route, which takes into account several factors, including traffic jam. What happens when we need to move data from point A to point B over a data network? To reduce the electricity consumed by data networks, we need to minimize the distance covered by our data when traveling over the network. That is, we need to reduce the number of hops from point A to point B, like we do with Google Maps. To achieve this, we need to have our servers placed right next to our customers. So, for example, if most of our users are located in Ukraine, then our servers must also be located in Ukraine or close to it. We don't want our data to travel around the world. It's even more efficient when we don't transfer our data, but instead process them right at their source, at the edge. So don't transfer your data if you don't need to, but instead process them right where they are being generated. Besides minimizing the distance traveled by data, we also need to minimize the size of data sent over the network. We can do this by filtering out any unnecessary data and always compressing our data before sending them over the network. Remember, energy-efficient applications do not send their data traveling around the world. When choosing the location that will host your software applications, make sure that this is close to your end users. What other factors should you consider when choosing the location of the data center that will host your application? We just mentioned proximity to end users. Some locations consume electricity that comes exclusively from burning oil or coal, hence having high carbon emissions. Other locations may consume green electricity that comes from the sun or the wind, therefore having zero carbon emissions. Google Cloud provides data about the mix of carbon-based and carbon-free energy in each region, therefore enabling us to choose the greenest one. Even if the users of your application are not located near any of these green cloud regions, then you could run your batch jobs on the cleanest option. We explained how choosing the right location for our data centers can help us consume greener electricity. How can we reduce the amount of electricity consumed by data centers? Here is a diagram of your data center showing the servers that host your software applications. Up to 50% of the servers running in your data center are idle. They just waste energy. These are redundant servers that just wait for a failure to happen so that they can take over and handle customer requests. But in the meanwhile, they are idle. They just wait, consuming electricity, consuming energy. Let's take a closer look. When failures happen to our applications, for example, a hardware fault in a server, we don't want our end users to notice this failure, but rather wish to continue doing business as usual. For this reason, we usually have one or more redundant servers that are in a standby mode doing nothing other than waiting for a failure to happen to the active servers so that they can take over and handle all the subsequent requests. As displayed in this diagram, upon failure of server A, a failover is performed to the previously idle server, which assumes responsibility to fulfill new user requests. Speaking of redundant servers, this is a car that features two engines for redundancy. It has one engine in the front of the car and an identical engine in the rear of the car. It even has two separate petrol tanks, again for redundancy. It was designed specifically for safari trips in the desert Sahara, where a failure in your engine could be fatal. If you plan to go for a trip to Sahara, then you should definitely choose a car with two engines for redundancy. But when you go to the cloud, your applications don't need to have redundant servers. Can you think of an alternative high availability model for your applications that does not use redundant servers? With the advent of cloud and containers, Docker ones or alike, we can enable a new high availability model for our applications that does not use redundant servers. One of the main characteristics of containers is that they have a size in the range of several megabytes, which is orders of magnitude smaller than virtual machines, which have a size in the range of several gigabytes. Similarly, lightweight containers have a startup time of several seconds, which is again smaller compared to virtual machines, which have a startup time of a few minutes. The established practice of using redundant servers is due to the time that it takes to spin up a new server instance, that is, a new virtual machine, when a failure occurs to the active server. If users had to wait for several minutes for a new virtual machine to start, then the failure would be noticeable by our users. But if this application were containerized, then a new container instance could be started in a fraction of time, therefore allowing for a seamless failover without the end users being able to notice this failure. As shown in this diagram, by containerizing your application, you can adopt a new high availability model that does not use any redundant servers. As soon as there is a failure in a container instance of your application, you can quickly spin up a new container instance. Moreover, public cloud providers enable us to run these containers without having to worry about the underlying infrastructure, without having, for example, to provision or maintain any virtual machines for these containers to run on. Concluding, by containerizing your applications and running them on a public cloud provider, you can adopt a new high availability model that reduces the resources consumed by your applications, therefore reducing both your cloud bills and the environmental footprint of your applications. And remember, when you go to the desert for a safari trip, always choose a car with redundant engines. But when you go to the cloud, you don't need redundant servers. Speaking of cars, modern cars are equipped with a stop-start system that stops the engine when it's not needed. For example, when you are stuck in a traffic jam or when you wait in front of a red traffic light, they stop the engine so that they reduce fuel consumption and therefore reduce carbon emissions. Older cars did not have this system, which meant that the engines would keep on working even though they were not needed when they were idle. Can you think of a similar example for software applications? Can you think of a case where software applications do not serve any requests, but they just wait? And although they wait, they consume resources, they consume CPU, they consume memory, they consume electricity. If you have applications that are idle most of the time, waiting for an event to happen so that they can start processing something related to this event, then this is a sign that you can have your applications re-architected to adopt the function as a service paradigm, which works as a stop-start mechanism. Our goal here should be to minimize the idle time of our applications, therefore increasing the utilization of our compute resources. Applications that leverage functions as a service, as a paradigm, are only executed in response to requests or events. They run just for a short period of time until this event is processed, and they are next terminated if there are not any other requests pending. As displayed in the diagram, an application is broken into individual functions, with each one of them doing a single independent piece of work. Each function may be triggered by an event, such as an HTTP request, or a file uploaded to cloud storage, or a new event arriving in a queue, or it could be a task scheduled to run at a given time, like a cron job. Clearly, when adopting the function as a service model, our application does not run as a whole, but individual functions are executed instead. This means that by adopting this model, we are transitioning from long-lived applications to short-lived functions. Function as a service falls under the category of serverless architectures, which means that software engineers can focus only on writing applications without having to manage or provision any servers. The cloud provider takes care of all the underlying infrastructure, also handling automatically the scaling of our applications when, for example, there are multiple incoming HTTP requests. Likewise, the cloud provider takes care of scaling down to zero all our functions when there are not any requests pending. All the public cloud providers allow us to run serverless functions. As an example, Microsoft Azure allows us to write functions in one of the programming languages shown here in this slide. We should be avoiding long-running functions as the default timeout is set to 5 minutes. If your favorite programming language is not supported by serverless functions, then you can use a managed cloud service that allows you to run code written in any programming language as long as it is packaged in a container. Amazon services Fargate, Azure Container Apps, and Google Cloud Run are all examples of such services that help us run our containerized applications without having to provision or maintain any infrastructure. These services support long-running tasks that can run for days or weeks therefore offering more flexibility compared to serverless functions. As we learned, modern cars have introduced a stop-start mechanism to make our cars more fuel efficient. You can do the same with your software applications by introducing a stop-start mechanism, that is, by leveraging a function as a service. Speaking of cars, we have different types of cars depending on the fuel that they consume. For example, some cars consume petrol, others consume diesel. Nowadays, we even have electric cars. Some of them are friendlier to the environment compared to others. What happens with software applications? Is there some kind of fuel for software applications? What could this be? Different applications are written in different programming languages. Let's think of the different categories of programming languages that we have. We have compiled languages like C and C++. We have languages running on virtual machines like Java and C#. And we also have interpreted languages like JavaScript, Python, Perl, and Ruby. Some programming languages consume less energy than others. Can you guess which ones? According to academic research, compiled languages tend to be the fastest and the most energy efficient ones. C, Rust, and C++ are the most energy efficient programming languages, whereas Ruby, Python, and Perl are the least energy efficient ones, with Perl consuming 80 times more energy than C. If your application uses one of the most energy efficient languages, then you're fine. But what can you do if your application happens to run in one of the least energy efficient languages like Ruby, Python, and Perl? Should you rewrite your application? It depends. If your application is being used by many users, for example, internet scale applications, then you should identify one or more components, one or more modules that consume the most energy, and then make a decision if you need to rewrite them in an energy efficient language. Speaking of programming languages, Java is today one of the most popular languages for the development of enterprise applications. According to a survey conducted by JetBrains, Java ranks as the second primary language being used by professional developers, with 72% of them still using Java version 8, although the latest version is Java 17 as of September 2021. Modern versions of Java have introduced several enhancements that reduce the memory footprint of our Java applications. Since Java 9, the memory allocation for string objects has been enhanced, consuming up to 50% less space, especially for strings consisting of Latin characters. According to some tests, we can have performance improvements of up to 10% just by upgrading to Java 9. For more information, you can read my article on my blog. Likewise, since Java 10, Java applications running on the same host can take advantage of class data sharing to reduce the memory footprint up to 15%. This feature is especially useful for microservices built on the same Java stack. Again, for more information, you can refer to the article I've written on my blog. Nowadays, there are several distributions of Java available, such as Amazon Corretto, Azul Zulu, Eclipse Adoptium, which was previously known as Adopt OpenJDK, and IBM Semeru. One difference that is often overlooked is the Java virtual machine that these distributions of Java rely on. Most distributions, such as Eclipse Adoptium, rely on Hotspot. This is the virtual machine that has always been released together with Oracle's JDK, and it is the most widely used one today. IBM's distribution is based on Eclipse OpenJ9, which claims to have a lower memory footprint and a faster startup. According to some experiments that I have run, as you can see them here in this diagram, when running an open source application, Spring Pet Clinic, OpenJ9 indeed had a lower memory footprint. Clearly, running your Java applications on OpenJ9 can have a lower impact on the environment, given that less resources are consumed, while at the same time, it can also help you cut down on your cloud bills. Concluding, to make your Java applications more energy efficient, you need to upgrade to a modern version of Java, preferably the latest one, Java 17. Additionally, it is worth considering migrating to a lightweight Java virtual machine like OpenJ9. When running applications on the cloud, we are being charged based on the resources consumed by our applications. The more network traffic consumed, the more we pay. The more the CPU and RAM usage, again, the more we will pay. As a rule of thumb, reducing the cloud bills of our applications implies that we are making our applications more energy efficient since they are consuming less resources. All public cloud providers have established frameworks of best practices that assess your applications against several criteria, including cost and performance. As an example, Azure Well Architected provides a score for your application with cost-optimized applications ranking higher. By following these recommendations, especially the ones regarding cost, you can reduce the resource consumption of your applications, therefore reducing their carbon emissions at the same time. Let's summarize all the actions that you can take to make your software applications more sustainable. First of all, especially for Java applications, you need to upgrade to the latest version of Java. Additionally, you may consider migrating to a lightweight Java virtual machine such as OpenJ9. Next, it's about the data that you transfer over the network. You need to choose the shortest distance and always compress your data to minimize their size. Next, you need to get rid of redundant servers. You don't need redundant servers on the cloud. Next action is to introduce a stop-start mechanism in your software applications by transforming long-lived applications to short-lived functions. And the last item is to identify energy-consuming components and rewrite them in an energy-efficient language. Here, the overarching theme is reducing the cost of your applications running on cloud. By doing this, you are likely making your applications more sustainable, more environmentally friendly. Now it's your turn. What actions will you take to help prevent climate change? How will you improve your software applications to make them more sustainable? Scan this QR code using your mobile phone and tweet your answer.
Hi, Ioannis, one more time. Sorry for waiting. Let me invite you to the discussion table to continue speak about your topic with our participants.
Thank you.